Imagine generating strings using only 3 characters, A, B, and C. But there's one strict rule. No 2 adjacent characters can be the same. Strings like AA or BB are forbidden. These special strings are called happy strings. Now here's the challenge. If we list all happy strings of length n in lexicographical order, what is the kth string in that list? Brute force works. But there's a much smarter mathematical trick that lets us jump directly to the answer. Let's break it down. A happy string must satisfy only characters A, B, C. Adjacent characters must be different. Example for n equals 2. Valid happy strings. A B, a C, B, BC, C, CB. Invalid strings. BB, CC. Let's count how many happy strings exist. For the first character, we have 3 choices, A, B, C. For every next character, we cannot repeat the previous one. So we have 2 choices. Therefore, the total number of happy strings is 3 times 2 to the power of n minus 1. Example, 4n equals 3. 3 times 2 squared equals 12 happy strings. Lexicographical order is, for n equals 3, the order looks like this. 1 AB, A2, ABC, 3 AC, A4, ACB, 5B, AB, 6B, AC, 7B, CA, 8B, CB, 9C, AB, 10C, AC, 11CB, A12, CBC. The K equals 9. The answer is CAB. Approach 1, backtracking. The intuitive solution is depth-first search, also known as backtracking. We build the string character by character. Rules. 1. Try characters in order of BC. 2. Skip the character if it equals the previous one. 3. Stop when we reach the kth string. Here is the backtracking implementation. Class solution. Define function getHappyString with parameters n and k. Create an empty list called res. Define a helper function called dfs that takes string s. If the length of residential is greater than or equal to k, return. If the length of s equals n, append s to res, then return. Loop through characters a, b, and c. If the string is empty, or the last character of s is not equal to the current character, call dfs with s plus that character. Start the search by calling dfs with an empty string. Finally, return the k-1 index of res. If k is less than or equal to the length of res. Otherwise, return an empty string. Time complexity, O of 2 to the power of n. Space complexity, O of n. This works because n is less than or equal to 10. Now here's the trick interviewers love. Instead of generating every string, we can skip groups of strings. Each prefix produces 2 to the power of remaining positions. Strings. So if a block contains more strings than k, we skip it entirely. This allows us to directly construct the kth string, and this reduces the complexity to O of n. Now let's look at the optimized implementation. Class solution. Define the function getHappyString with parameters n and k. First, compute the total number of happy strings. Total equals 3 times 1 shifted left by n minus 1. If k is greater than total, return an empty string. Initialize result as an empty string and previous as an empty value. Now iterate through positions from 0 to n minus 1. For each position, calculate the block size as 1 shifted left by n minus I minus 1. Then try characters A, B, and C. If the character equals previous, skip it. If k is greater than the block size, subtract the block from k. Otherwise, append that character to result, update previous, and break the loop. After finishing all positions, return result. This problem teaches 2 important patterns. 1. Backtracking. Generate combinations under constraints. 2. Combinatorial skipping. Jump directly to the kth lexicographical result. The same idea appears in kth permutation problems, combinatorics, ranking permutations, And that's how we find the KTH happy string efficiently. If you enjoyed this breakdown and want to master LeetCode patterns faster, subscribe for more coding explanations like this. See you in the next problem.